I am going to talk about nuclear deformation from a theoretical perspective. And the main reason why I am coming back again to talk about nuclear deformation is because I am not very convinced of the use of intrinsic deformations in order to explain the data that people are obtaining in these ion collisions, right? So in principle, one should use the laboratory frame densities in order to perform these calculations. I mean, these calculations that people are usually performing in order to reproduce experimental data. And the connection between this laboratory frame and intrinsic frame densities that are used is not straightforward to me. And I think it's not straightforward to anybody in the audience. So this is why I want to stress again that one has to use, in principle, these laboratory frame densities, or try to find a connection between the laboratory frame densities and the intrinsic ones that are used in the current calculations. So let me first go very quickly to a very brief introduction. Well, probably all of you already know that the motivation for this kind of studies is because in these heavy ion collisions at high energies, a lot of particles are produced, and then when one analyzes those, the flux of those particles by using hydrodynamic ideas, it turns out that you can explain many of the experimental data by using very simple, by using simulations, not very simple simulations, but simulations that use a very simple approach for the starting condition. So essentially, for the easiest and the simplest situation where we have two lead-208 colliding with some impact parameter here, we consider for the simulations that the lead-208 is made of protons and neutrons. Those protons and neutrons are distributed according to a spherical density, right, as it corresponds to lead-208. And then the hadronic interactions taking place in the modelization of this process lead to some flux of emitted particles and this and that, right? So what people is doing in these simulations is essentially use a matter distribution that is following the parameterization of the Booth-Saxon potential. So it has this shape. And while in the case of lead-208, there is only one parameter in order to characterize the density. That is essentially the radius and eventually the thickness of the skin of the lead-208. Things are slightly different when we are making collisions between the form systems. So in this case, it is assumed that for some unknown reason, one can use the intrinsic density. That means that we have to use a deform density as the starting condition. So as I will argue later, this is not a physical density, right? This is just the consequence of an approximation. And in principle, one should use the laboratory frame density, the density associated to the real wave function of the system, right? Apparently, there is, I mean, one can use unwavering arguments and say that the use of the intrinsic densities is guaranteed because one is taking an instantaneous picture of what is happening in the nucleus, and this somehow justifies the use of intrinsic density. Okay. So if one assumes that it's possible to use the intrinsic densities, then we have to parameterize those densities for the form systems, right? And then we have to introduce additional parameters, now the theta and phi angles, and we have to parameterize the density, the shape of the density with this Booth-Saxon parameterization that involves several deformation parameters like the quadruple deformation. Can you see my pointer?
Yes. Yeah.
Yeah, okay. So you have the quadruple deformation parameter that is associated to the shape. You have the triaxial deformation parameter that is associated to some triaxial deformation, departure from axial symmetry, octuple deformation that is associated to the breaking of reflection symmetry along this plane, and then hexadecupole deformation that is associated to these diamond-like shapes, right? Then by using this more general density for the initial condition in the simulations, it's possible to reproduce very nicely experimental data, not only for spherical systems like in the previous example of LED 208, but also in some other examples in corresponding to experiments that have been performed mostly at RIC, but also at the LHC, that correspond to the form nuclei like this xenon 199, gold, uranium, ruthenium, and zirconium, right? In some of these cases, the nuclear deformation, intrinsic nuclear deformation, involves triaxial deformation, like in this xenon 190-29, hexadecupole deformation, like in the uranium case, or octuple deformation in the case of the zirconium. So here we have an example, right, of the comparison of experimental data that is obviously given by these blue dots or the squares, the pink squares, and the results of the simulations using different deformations for the initial condition in the collision. And here we have the ratio between the xenon-xenon collision to the lead-lead collision. And we can see that in order to reproduce experimental data, one has to assume a deformation for the xenon system that is corresponds to the quadrupole deformation of 0.2 and triaxial deformation gamma equal 30 degrees, right? So you can see that really by using these ideas of using the intrinsic density, one can reproduce very nicely the experimental data. The situation is also the same in the case of these isobar collisions that were presented and discussed recently in 2021. In those cases, one expects that the physics corresponding to one of the isobars is going to be exactly the same as the physics corresponding to the other isobar, and therefore the ratio of quantities must be equal to 1, right? And there are really very big deviations from this ratio equal to 1 in the experimental data. And those deviations imply that, for instance, ruthenium-96, well, these experiments are performed for ruthenium-96 and the isobar zirconium-96. Well, the experimental data indicates that ruthenium-96 is strongly deformed, quadrupole deformed, and zirconium-96 is octuple deformed. So the trivial conclusion, as probably you have heard many times in this program, is that low energy nuclear structure data can be extracted from heavy ion collisions, right? But the question, and this is the main caveat I want to discuss, is the fact that the intrinsic shapes and the deformation parameters that we use to describe them are not physical observable. So they are just constructs of our theoretical interpretation of nuclear data, and therefore one has to try to connect both worlds, right? So let me first, in order to make this connection very quickly, go through some very basic facts about quantum mechanics, right? So don't be scared by the amount of words in the transparencies. I will go very quickly through them. So it's very well known that if a system has a given symmetry, if the Hamiltonian commutes with all the operators of the symmetry group. So in the case of parity, it means that Hamiltonian commutes with the parity operator. In the case of rotational invariance, it means that the Hamiltonian commutes with the rotation operators for all possible Euler angles characterizing the rotations, right? In this case, in the later case, as we are dealing with a continuous symmetry, the Hamiltonian also commutes with the generators of the symmetry. So in terms of group theory, we are dealing here with the group, and in this case, when we are talking about the generators, we are dealing with the algebras of the associated Lie group, right? So the consequence of these commutation relations is that we can use the quantum numbers of the symmetries in order to label the eigenstates of the Hamiltonian. So in the case we have reflection symmetry as a consequence of the Hamiltonian being reflection symmetric, parity is a good quantum number, and we can use it to characterize the quantum numbers of our eigenstates, right? This is the case, for instance, when we say in nuclear physics 100 that the ground state of all even nuclei is 0 plus. I mean, the plus is the parity of the corresponding ground state, and is positive because the Hamiltonian commutes, the strong interaction Hamiltonian commutes with the parity quantum number, right? The same happens with rotational invariance. In this case, things are a little bit more involved because the symmetry group in this case is not abelian. Then one has to deal with some peculiarities of this algebra, and then the quantum numbers are the angular momentum quantum number and the third component of the angular momentum along the z-axis, right? So there are a couple of things that have to be taken into consideration when thinking about these facts. One is that this is only valid for stationary states. So if we have some time-dependent evolution in our system, this is no longer the case for the wave function of the system. And also, we have to deal, in the case of having degenerate eigenstates of the Hamiltonian, we have to deal with those degenerations, because in that case, it's possible that the quantum numbers of the symmetry cannot be used as quantum numbers of the eigenstates of the Hamiltonian. Typical case is what happens with electric dipole moment in the n equal 2 level of the hydrogen atom, and this is what is behind this concept of hybridization in atoms, and that is discussed in chemistry, right? So in principle, the idea is if the Hamiltonian is having a symmetry, then we can use the quantum numbers of the symmetry to label the eigenstates of the Hamiltonian. This is a very basic fact of quantum mechanics. So we are dealing now with what is happening in nuclear physics. And in nuclear physics, we have, first of all, a very fruitful concept that is the mean field concept, right? That is rooted in the fact that we have to explain in a natural way the magic numbers. So by using a mean field, we are able to grasp most of the correlations present in the nucleus wave function, right? The mean field can be obtained by means of the Hartree-Fock or the Hartree-Fock variational approximations that are really approximations to the full many-body problem. And those approximations do not have to preserve the symmetries of the Hamiltonian. In this case, we say that the approximation, the mean field approximation, is spontaneously breaking the symmetries of the Hamiltonian, right? And this is exactly the same mechanism as in quantum chemistry or in atomic physics when people talk about unrestricted Hartree-Fock, right? If you are familiar with unrestricted Hartree-Fock, this is essentially the same mechanism, right? By breaking the symmetries at the mean field level, in this approximation, we are incorporating many correlations into a simple mean field picture. And the mean field picture is very simple, mostly because it incorporates in a natural way the symmetrization principle. That is something that is in principle very difficult to accommodate into a general description of a general wave function because it involves n factorial terms in order to antisymmetrize or symmetrize a given wave function for a system made of n particles, right? So we say, and this is some language, that the symmetry breaking mean field solutions live in what we call the intrinsic frame and are denoted intrinsic wave functions. And the word intrinsic is just used here to emphasize the fact that this is the result of an approximation. It's not a physical system, it's just some kind of construction in order to accommodate this mean field approximation we are talking about. According to Wigner, right, Jean Wigner, the father of symmetries in quantum mechanics, linear combinations of rotated deformed intrinsic wave functions can restore proper quantum numbers of, in this case, angular momentum, right? So this is a well-known fact, and this is what we use in nuclear physics in order to go from this intrinsic frame to the laboratory frame. So the idea is that at the end, the eigenstates of the Hamiltonian have the quantum numbers of the symmetries. The mean field approximation that is grasping a lot of correlations in the wave function of the nucleus is not having the proper quantum numbers because the symmetry is broken. So in order to go from one picture to the other picture, we have to restore the broken symmetries. And to restore the broken symmetries, we use a procedure that is rooted in group theory, right? We will see an example later on if I have time to discuss parity restoration. But the idea is that you have this wave function that is this psi on the left-hand side of this equation, that is a wave function with the proper quantum numbers of the symmetry of the symmetries of the system, that is given in terms of some symmetry restoration operators acting on the intrinsic wave function, right? So there is a connection between the physical wave function and the intrinsic wave function, right? But this connection is really not straightforward. So you cannot forget about these projection operators in any way in order to go from one frame to the other frame. By the way, in the frame with all the quantum numbers, with wave functions with the proper quantum numbers, we say that we are working in the laboratory frame because this is the frame of reference corresponding to nature, right, to the laboratory. So the projectors are linear combinations of the symmetry group elements. We will see an example. And what is important is that physical observables have to be computed with the symmetry restored wave functions. They cannot be, in principle, computed with the intrinsic wave functions. So mean values, mean field values, or transition probabilities have to be computed with the real wave functions in the laboratory frame. So if you are not convinced about this speech, just think about what probably you know about the shell model approach, the interacting shell model approach. Probably you have heard about the interacting shell model approach, and you know this is a very powerful method that is able to give you a solution, an exact solution of the problem, but in a restricted configuration space. And the shell model doesn't need to go to the intrinsic frame, doesn't need to introduce any intrinsic deformation in order to obtain the exact, within this configuration space, the exact wave functions of the system. And then shell model is a very well-known method to solve the nuclear many-body problem, right? Okay, so then in this attempt to go from the intrinsic to the laboratory frame, we have to remember also the rotational model that Bohr and Mottelson proposed in the 50s, and that was what led them to get the Nobel Prize a few years later, right? And this rotational model is just an attempt to go from the intrinsic to the laboratory frame. And the idea Bohr and Mottelson had at that time was just to introduce some kind of additional degrees of freedom into the intrinsic description. And these additional degrees of freedom are just orientation wave functions. They use orientation wave functions in the form of Wigner functions. And these orientation wave functions were decoupled from the intrinsic ones. By using these ideas, one has to really integrate on the orientation wave functions. You can compute within this model physical quantities that are given in the laboratory frame by using this wave function model. In this case, you obtain expressions like this one that I have just directly copied from this nuclear many-body problem book by Rini Shook, where you have this matrix element in the intrinsic frame corresponding to a multiple moment of order lambda. This is the kind of quantities that enter transition probabilities, right? And you can prove within the realm of this model that this quantity in the laboratory frame can be given by this linear combination. Well, you have here some class 3J coefficients and some extra coefficients times these quantities that are computed in the intrinsic system. So there is a relationship, right, in Bora-Mottelsol model between the intrinsic quantities and the laboratory quantities. In fact, if we use this expression and we restrict it to k equals 0 bands and we used quadrupole transitions, we obtain this very famous formula that relates B2 transition probabilities. Oh, sorry, here I forgot an arrow and an I here. This is the transition from I plus 2 to I, right? This E2 transition probability is given by some geometric factors times the mean value of the quadrupole moment in the intrinsic frame, right? So, and this quadrupole moment in the intrinsic frame is just given in terms of the beta deformation parameter that is used very often to characterize deformation in the intrinsic frame, right? So, but Bora-Mottelsol rotational model that is very successful in interpreting many experimental data, like the physics of rotational bands, is nothing but a model, right? So you have to try to make a connection, a microscopic connection with the previous theory we were talking about in the previous transparencies. And it can be proved, and it's not difficult, that in the strong deformation limit of the intrinsic wave function, that means the intrinsic wave function is very well deformed, in this strong deformation limit, you can work all the expressions with the projectors, all the very sophisticated and involved expressions with the projectors, and you can remove all of them, I mean the projectors, and you end up with the results and the predictions of the Bora-Mottelsol model. So it means that starting from a fully microscopic theory, you can go to the Bora-Mottelsol model by using this strong deformation limit, right? So there is a connection, but you have to use some specific conditions, some specific assumption, that is the strong deformation, right? So once I have said this, I have to just discuss or mention some reflections about what I have said before, right? So it's very interesting in order to get a better understanding of what is going on, to to analyze the changes that are produced when we use the density in the intrinsic system and the density in the laboratory system, right? This is something that has been done in a couple of examples. I will show you some of the results, but this connection is not very clearly established, right? Mostly because it's computationally intensive, but it's not that intensive. So we will do this kind of calculations in the future. And then it will be required to analyze the role of using the lab density in the Glauber Monte Carlo model used to study the experimental results, right, in these simulations that are so successful in interpreting the heavy ion, high energy results, right? Then this kind of analysis would be useful in order to interpret this zirconium 96 puzzle. And I say puzzle because in principle, according to this heavy ion data, zirconium 96 is strongly octupole deformed. According to nuclear structure calculations, is not what I would call a strongly octupole deformed system. It has some octupole deformation, but it's a dynamic octupole deformation that in the ladder of deformations in the intrinsic system is not at the highest in this ladder. Intrinsic deformation. So it's usually when we talk about deformations, we are talking about static deformations where you have a real minimum at the midfield level, and this is not the case in most, if not all, the nuclear structure calculations for zirconium 96. Okay, so let me.
I have a question. You know, in this approach, when you write down the wave function, this is the collective wave function, but I just wonder, is a way to write down a two, like instead of a single body wave function, is something that can be done, like write down directly n-body wave function. So then you will contain you don't need any reference frame anymore, right? Just write it.
Yeah, I mean, the idea, no, the idea is that what I call the laboratory frame. I mean, this is not a real frame of reference like when you talk about frame of references in dealing with Galilean invariance or something like that. It's just a matter of language, right? So it's just to differentiate when we talk about the laboratory frame, to differentiate between description based on wave functions with the correct quantum numbers associated to the symmetries of the Hamiltonian. Whereas we talk about the intrinsic frame when we are breaking those symmetries, that is in principle not allowed in quantum mechanics. But we allow this symmetry breaking because it's very convenient in order to accommodate additional correlations into our very simple mean field picture, right? So really the laboratory frame and the intrinsic frame are not really frames of reference. You cannot go, I mean, you can go from one or to the other because you go from one to the other by doing this symmetry restoration, right? But they are not really.
As the mean field picture, the mean field picture captures all correlations, because if it's mean field, there are some correlations you may not be able to capture, right?
No, I mean the mean field picture captures most of the correlations, but obviously it's not capturing all the correlations, because in order to capture all the correlations and go to the proper wave functions of the system, and those wave functions must have the quantum numbers of the symmetries of the Hamiltonian, you have to include some additional correlations that are incorporated by means of this projection operator, right? The question is that the correlations incorporated by symmetry restoration are usually less intensive, if you allow me to categorize correlations in terms of intense or less intense correlations, right? But are less important than the correlations introduced into the description by breaking the symmetries of the mean field, right? So in principle, I mean, it's something that probably you may think that this is just some kind of elucubration, right? Theoretical elucubration, but I think it's important, right? Because I mean, one has to work things in the proper way, right? So if the principles of quantum mechanics tells you that the wave function must have the quantum numbers of the symmetry of the Hamiltonian, you cannot avoid that, right? Okay, so I was planning to discuss octupole deformation, right, in connection with zirconium 96, but I see that I have already used most of my time, right? I have almost used half an hour. So if you give me 5 minutes, I will go very quickly into this discussion of octupole deformation, right? So I will skip a lot of transparencies because they are just giving a terse introduction to the physics of octupole deformation in nuclear structure. So there is no need to discuss that things. But this is, for instance, this transparency is important because here we are studying the mean field energy obtained in the Hartree-Fock-Bogoliubov approximation in terms of the beta-3 deformation parameter. And we see 3 typical examples where we have this gadolinium-158, lead-208, and radium-224. And it's only in the case of radium-224 that we are gaining some energy at the mean field level by letting the system acquire some non-zero octupole deformation. So this is the kind of systems where we say that there is a static octupole deformation, right? And the reason why there is this static octupole deformation in this specific isotope is because here proton and neutron numbers correspond to these octupole magic numbers, right, that are given here, that correspond to those situations where the Fermi level, we have some specific orbitals above the Fermi level and some other specific orbitals with some specific properties below the Fermi level. In this case, octupole correlations are enhanced, and then you have enhanced octupolarity at the mean field level. If you study this kind of plots for all the nuclei in the nuclear chart, you get this diagram here that is telling you the energy gain by letting octupole deformation being different from zero at the mean field level. And you see that the amount of nuclei where octupole deformation is really relevant and is giving you some amount of energy that is in fact very small compared to the energy scales of a nuclear structure, is just in some specific isotopes around the radium region. This is around the barium region, and here are some other isotopes, right? So the number of nuclei where octupole deformation, static octupole deformation, is observed in the calculations, in the mean field calculations, is rather limited, right? So here we have exactly the same, but then, okay, here is the single particle levels that are involved in these strong octupole correlations, here in red and in blue, but I'm going to skip this. But then if we restore the symmetry, because we can restore the symmetries of these octupole deformed systems, we have to use these projectors. In this case, it's very simple because the projector is just the linear combination of the identity here plus the parity operator, and the weights are essentially just the parity quantum number we want to project into the intrinsic wave function, right? So this is again rooted in group theory, but in this case, due to the fact that parity is a discrete symmetry, the projector is extremely simple, right? So then we can project to positive parity and negative parity these intrinsic states, and we obtain these blue and red curves, blue and red curves, blue and red curves in the three cases we were studying before. And we see that for positive parity, the blue curve, we are gaining some energy by projecting, intrinsic states with an octupole deformation different from zero. And for negative parity, we are also having a solution, right, that is different from the positive parity one. It's also having a minimum here at an energy that is obviously higher than the positive parity one, but is taking place for an octupole deformation different from the ground state. Even in the case of lead-208, you have an energy gain by letting the intrinsic system to deform with some octupole deformation, right? So even in lead-208, that is the paradigmatic example of an spherical nucleus at the midfield level, you have some energy gain by letting the intrinsic system to deform and then restoring additionally the symmetry. Obviously, in this case, where you have static octupole correlations, there is no gain by projecting onto good parity. Right here, you are essentially in the strong deformation limit I was mentioning before, right? So you can generalize this kind of ideas of symmetry restoration by incorporating fluctuations in the octupole degree of freedom, but I'm not going into these details. Just let me tell you that when you take into account this correlation energy coming from parity projection, the picture at the midfield level of nuclei that are gaining some energy because of static octupole correlations change substantially, and instead of having just a bunch of nuclei gaining energy, we have that all these nuclei in the nuclear chart, essentially all the nuclei considered in the calculation, are gaining some energy by considering symmetry restoration. So by restoring the broken parity symmetry, we are gaining some energy. Usually the energy gain is not as large as the static octupole correlations, but it means that if we include this dynamic, what I call dynamic octupole correlations, we are having dynamic octupole correlations everywhere, even in lead-208. So one has to be careful with what one means with intrinsic system, right? Intrinsic system associated to static deformations, intrinsic system associated to dynamic deformations. So, I mean, the situation is not as clear as it may look like with less involved considerations. So this is the result of some calculations I have performed for this zirconium 96 and ruthenium 96 with some state-of-the-art effective interactions by considering the quadruple and the octuple degrees of freedom. And you see that at the mean field level, right, as I said before, both zirconium and ruthenium 96 are not octuple deformed. But what is more important is ruthenium 96 is not quadruple deformed at the mean field level. So it doesn't have a quadruple deformation at the intrinsic, at the static level. However, if we consider parity restoration in the case of zirconium 96, this mean field picture changes to this picture for the positive parity projected energy, and this picture for the negative parity projected energy. So we see, as we were obtaining in the previous transparencies for the one-dimensional case, that indeed we are gaining some energy by allowing the system to deform in the octuple direction slightly, both for the positive parity projection and also for the negative parity projection. So here you have some pictures of the densities obtained for this positive parity minimum. It corresponds to beta 3 0.1 and beta 2 equals 0. This is the mean field intrinsic density, and this is the density you obtain after projecting the wave function and the density associated to the projected wave function. And you see here the differences between the two densities. Here the difference is in the same color scale, but has to be multiplied by 50 in order to have something different from blue, right? And here is the same for beta 3 equals 0.2. So really you see that going from the intrinsic to, let's say, the laboratory densities, you have some changes that are important, can be visualized in terms of these density differences, but the connection between these two is not really straightforward, right? So this is not restricted to parity symmetry restoration. It's also the case when one is restoring rotational invariance, as you can read in this Physical Review C paper back to 2012, right? Here we are, these people were restoring the rotational invariance of this deformed system, this silicon 34, and here you see that the wave function projected to angular momentum 0 obviously has spherical symmetry as it should have, right? And if you look at the density as a function of the radial distance, you see that the projection is bringing some differences with respect to the intrinsic wave functions, the intrinsic densities, excuse me. So really, one has to take into account this consideration. But the point is, well, this is what one should do in principle in order to deal appropriately with symmetry restorations, in this case of octuple and quadruple correlations. Probably Giuliano in the previous talk has already mentioned some calculations we have performed together for uranium 238, where we obtain some dynamic octuple deformation. Those calculations are performed in this framework. I am mentioning it here, but I'm not going to discuss this framework. I just presenting some results we obtained for barium 244. That is one of the paradigmatic examples of octuple deformed systems. So thank you very much for your attention. I hope I have called your attention to this, in principle, formal problem, but a problem that I think deserves some consideration, because the connection, in my understanding, from the laboratory to the intrinsic frame is not yet well established, right? So thank you very much.
Questions? If none, I just have a real quick one maybe. So the argument is that these me field deformation parameters, for example, are model dependent, like they're not physical, right?
Yes, this is my point.
About what the separation between static and dynamic deformation. Is this something that's well defined, or is this also a model dependent sort of concept?
Yeah, it's some kind of model dependent, thing, yes. So I mean, the classification, whether a deformation is static or dynamic is model dependent, is what you consider static or dynamic. I mean, essentially, the idea is that if you have a very well defined and very deep energy minimum as a consequence of a symmetry breaking, then you can speak confidently in terms of static deformation. But in the case of octoball deformation, all the mean field minima you obtain are very shallow, only a couple of MEV at most in depth, and this is not what we would call a well-deformed well, right? So, but in any I mean, in some way, yeah, this is also model dependent.
Okay, thank you. Uli?
I am still not clear about how you would recognize the form of the deformed energy density that is produced, say, in a heavy ion condition by your procedure. So you start out with the wave function in the lab frame, which is an energy eigenstate and an eigenstate of angular momentum and parity. And clearly, when I take such a wave function and I ask the question, if I measure one nucleon, it will be anywhere because this state rotates and everything. But after I've measured one and I measure the second, I will start to see a correlation. And after I've measured the 200ths, I will see hopefully the deformed configuration. How would you identify that in your calculations that you're planning to do?
Well, I have to be honest, I don't know. I mean, probably I should consider some kind of two-particle correlation function, right? Mm-hmm. And compute this two-particle correlation function using the laboratory frame wave functions. This is something that is in my to-do list, but it's not an easy task, right? And then I should try to find a connection between these two-particle correlation functions and the use of intrinsic density in the Glauber model, right? And this is also a connection that I don't know how to make. But it's true that in principle, one should consider two-particle correlation functions, probably or three-particle and in general, yeah.
I would take Uli's argument actually further and say it's actually the correlations that's the real observable that you're measuring. It's nothing more than that.
Mm-hmm.
Yeah, but I mean, my point is that there must be some connection between correlation functions and the intrinsic density, and this connection is not clear, or it has not been made. So my point is that we should spend some time, and perhaps I am one of the persons that should spend some time in trying to make this connection. But it's important to make this connection. I mean, we cannot forget.
But that's why I'm asking the question whether you capture all the correlations, because if we do a two-particle measurement in Cavian, we measure all correlations, right? That contribute to two-particle level. But if I take a mean field solution, I try to then bootstrap into some kind of two-point correlation.
Yeah, but look, in principle, but if you are using as your initial condition, the density in the intrinsic frame, I would say that you are taking into account mean field correlations.
Yeah.
Somehow, I mean, it makes sense. You are not using the density coming from the real wave function of the system. So there is something there that is not clear, And in my poor understanding, or in my in my understanding, it should be clarified. I mean, one has to pay some attention to this problem because it's not straightforward, but at the same time, it's not irrelevant, right? So, I mean, I would be happier if I would be able to understand in a firmer grounds this connection.
So in all the calculations, you are calculating just one nucleus, right? But in our equations, it's always two nuclei. Do you need to change the symmetry requirement, or is symmetry requirement from one nucleus to actually nucleus, two nuclei?
Well, I mean, my point again is you have to use, you have to consider wave functions with the proper quantum numbers, right? So how do you incorporate those into the Glauber model? This is an open question. So this is my point. And also thinking what I have said, I mean, most of the correlations, octupole correlations, are dynamic, at least in my calculations, right? So zirconium 96 has a dynamic octupole deformation like ruthenium 96. So what is making the difference between ruthenium 96 and zirconium 96, right? Both have a dynamic octupole deformation that are probably of the same size, and they are providing different, they have a different impact on this flux distribution after the heavy ion collision.
Okay, thank you, Luis.